Hello, everybody, and thank you for coming in for today's webinar. I am Mark Basher. I'm a manufacturing applications engineer here at GoEngineer. Been in the 3D printing additive manufacturing space, specifically supporting Stratasys products for close to 10 years now. Welcome to today's webinar. Today we're going to be focusing on Polyjet, what's recently been launched for the last half year of 2019. Got some really exciting new products. Just kind of want to go over them at a fairly high level, and then if you guys have any follow-up questions, anything like that, want more details, you'll get all of my contact info, and happy to follow up with some of those more details in the specific products of interest that you might have. So with that said, let's go ahead and get started. So GoEngineer, if you don't know, we've recently expanded some more through an additional couple acquisitions this year. We are now a coast-to-coast organization, expanding from the southeast, Florida, Georgia, up through the Midwest into Indiana, Michigan, and that carries all the way out to the West Coast, spanning from the Southern California border to the Northern Washington border, is now all territories supported by GoEngineer. If you don't know, GoEngineer, we really focus on selling the best engineering tools possible in the marketplace and help our customers use and get the most out of their investments in those tools. If you're not familiar, GoEngineer has a whole bunch of different products to support engineers. Our primary offering is SolidWorks 3D CAD software. We're the world's largest distributor for SolidWorks 3D CAD, but we have complementary products like Stratasys 3D printers, desktop metal 3D printers, also support the other side of the company where we have 3D scanning. We sell Creaform 3D scanners, Artec 3D scanners. And then we have a lot of different additional software pieces for simulation, product data management, and of course services that go with all of those products that we offer. In addition to the hardware and software product offerings, we also have trainings, certifications, and a lot of different online resources for our customers to use. We really focus on supporting our customers here at GoEngineer. We have an entire staff of customer support engineers for all of our products, and we maintain a hotline that's accessible for about 10 hours throughout each business day. In additional services we offer, the tech support, we do 3D printing training and 3D printing services for anybody who's maybe not in need of a printer but has a project-based need where we can help you guys out. So with all of the house cleaning items out of the way, I will jump into our agenda for today. So we have 4 simple things I want to talk about. These are all related to the Polyjet systems. The first item on the list is a Polyjet process overview. So if you don't really know what Polyjet is, you're a little bit unclear, I'm going to bring you up to speed so you understand what these new products are and the technology platform that they're operating on. Once we go over that overview, I'm going to talk about the brand new Stratasys J750 Digital Anatomy Printer. Then we'll talk about the brand new released Stratasys J850 printer. And we'll highlight the newest material release called VeroUltraClear. Polyjet process overview. Here we're just kind of looking at the full extent of the line of Polyjet systems. Polyjet 3D printers start as a single model material build unit that's kind of fits on a desktop or a benchtop. We call the Objet 30, and it goes all the way up to the brand newly released J850, which has roughly a 500 millimeter build tray and supports a whole bunch of different materials and mixes of materials and the applications that go along with it. To give you a kind of idea of where these things fall within a price range, you are in the $30,000 to $40,000 price range on the Objet 30, and you're going to get into the mid $300,000 range on the newest multi-material printers. So here we're looking at Stratasys' 3 core additive manufacturing technologies. People ask me, what's the best technology? And the reality is all of Stratasys technologies are very complementary in nature, in that something like the FDM gives us really robust mechanical and material properties, but, is limited to thicker layer resolutions and single material builds. The Polyjet materials, while they're not as robust as the thermoplastics like polycarbonate, Ultem, nylons, etc., They are very, very high feature detail type systems, printing very fine resolutions. And the fact that we can do so many materials at one time makes them very versatile and very good for simulating a lot of the products around us. Again, today we're looking at the Polyjet technology. A little history: the Polyjet technology was founded by a company called Objet in the early 2000s. Stratasys and Objet merged in the 2012 timeframe to sort of bring both products together under one roof. And the reason behind that is because, as I suggested earlier, they're both very, very complementary technologies and fill different niches within the marketplace. So it was a really good marriage when that happened about 7 years ago now. How a Polyjet system works is basically we're taking a similar piece of hardware that you would find in an inkjet style printhead. If you think of an inkjet style printhead, there's generally 4 material channels. We have cyan, magenta, yellow, and K or black. So CMYK is the typical configuration. And basically how these things work is the printhead scans over a piece of paper. The piezoelectric jets fire off the inks down to the page, and we produce an image or a text or whatever it is that is coming out of that printer. So what the Polyjet technology does is it takes that concept, but instead of applying just a colorized ink to land on, say, a white piece of paper, it's a piece of UV photocurable resin that is being jetted down with some finite thickness, and that produces, an individual layer of a build. Over many, many layers, we can use that to produce physical 3D geometries and physical parts we can touch and hold and view. So here we see the standard configurations for a multi-material Polyjet printer. This is the print block. This is kind of scanning across the x-axis in a planar motion. Jets are firing. The material comes down to the substrate or the workpiece. And then the UV lights that are flanking those print heads are causing that photocurable resin to harden as the machine moves on to the next layers. Here we're just going to look at a quick time lapse to maybe help you visualize how exactly this works. Head scanning, material flying out of the head, UV light curing it, and the part is growing. So after several minutes, or in the case of a very, very large part, many hours, we have a fully finished 3-dimensional model. And there we see the finished part. So introducing, we're going to start off with the Stratasys J750 Digital Anatomy Printer. So the high level here of what's going on is Stratasys took the J750 product and went through the process of developing some new materials, creating some new software, and coming up with some additional auxiliary support equipment to really aid in the ability of people to print medical models and anatomical models with a physical level of realism that's never been able to be done before. In the past, we have been able to do flexibles, we can do colors, we've been able to make things that sort of look like the real deal, but as it comes to simulating specific anatomical features, various types of bones and cartilage and discs and blood vessels, and we were just kind of guessing in terms of the properties. So this solution takes the J750 capability and it allows us to simulate the physical properties of anatomical models for a variety of different reasons we'll talk about in a second here. So here we see the J750 Digital Anatomy Printer simultaneously jets 6 model materials at one time. There's a few different printing configurations that change the layer thickness and the amount of materials supported. We have accuracy on this for up to 200 microns, and there's multiple bays within each material channel. So the machine can actually hot swap as one cartridge becomes empty, and it can continue building these massive medical models all at one time. It's going to retain all of the capabilities of an existing or a current J750 printer. By that same virtue, it's also upgradable from an existing J750 printer. So when you buy this printer, you're not having a limited device that just does anatomy. It is still a fully enabled system. The software processing the build trays on this is GrabCAD Print, which is the same software driving virtually all of the current Stratasys 3D printing systems. Part of this digital anatomy printer solution is a software license. So when you first get the system, that's included for 1 year, and then after that, it kind of goes to a yearly software licensing model. This is J750 Digital Anatomy Printer right now is really the tip of a long-speared initiative where I already know and I'm hearing there's going to be additional materials beyond the ones I'm going to highlight today that are going to get released on this platform. And then the algorithms and the specific anatomical areas that are supported are just going to really grow and build out. So the capability that we're seeing now is just the tip of the iceberg in what this product will become over the coming years. The first thing that gets us to this digital anatomy simulation is 3 new materials on this platform. So the first one is a gel matrix, the second one is a tissue matrix, and the third one is a bone matrix. With that, I'll kind of jump through and talk a little bit about each of the different matrices here. Bone matrix, the actual name for it is going to be called RGB 516. That's the standard naming convention for all the Stratasys Polyjet resins, RGB indicating that it's a rigid substrate. Ultimately, what this has done is it's deposited, at a voxel level to really simulate the structure of bones. There's 4 different regions that will get applied to a piece of geometry. And here on the screen, you see a couple different variations where we have that white material is the rigid bone matrix, and then that other material is a combination of Agilis and tissue matrix and other things like that to support the marrow sections that you'd find in the middle of the bone. And on the bottom, we see a little bit of a screenshot that actually comes from the GrabCAD print software. So, we're not just saying bone, but when we identify bones and various bone elements, and you see the list of elements there, the discs, the facets, the long bone, nerve roots, ribs, skull, etc. And then the software automatically applies a fill for the inside. We can, in this case, control and simulate the bone of somebody with osteoporosis or, stick with a healthy bone sample. This is really custom tailorable to the specific anatomy that we're trying to simulate. Moving on, the next material is the tissue matrix. So this is what gives us a very human-like feel. If you look here on the kind of comparison chart, the former Agilis material was the softest material offered on the Polyjet platform. That was on the Shore A scale of 30, so somewhere between a rubber band and a pencil eraser. While it was very flexible compared to the rigids, it wasn't very flexible in the total spectrum of flexibilities. The new tissue matrix, now on the Shore OO scale, that is somewhere between a gel shoe insole and an actual gummy bear. And that's what gives it the ability to replicate a lot of the human anatomies that are going to be used to do in the field. The third material is what we call a gel matrix. That's FLG110. This material has a very gel-like consistency. And the primary way that it's used is as we're going to simulate various vascular structures. The challenge in the past has been cleaning out those structures without damaging them in any way. So what this is doing is it's building that, what we call the blood pool in the medical industry, the blood that fills in the inside of a vascular structure. We're building that out of this gel material, which we can then subsequently clean out of those small channels with the new cleaning device that they've devised and launched with this product called the blood vessel cleaning apparatus, or the BVCA. Here's a quick video I'm going to play. This shows the gel matrix being cleaned out of a vascular structure. I think this kind of highlights it a lot better than I could explain with my own words. So this is not the blood vessel cleaning apparatus, but a colored liquid dye to sort of show how the cleaning fluid will be transmitted through the gel matrix, and ultimately the part will get cleaned. So because that's satisfying, we'll watch it one more time. But you look that, even through some of these smaller channels, they claim channels as small as 1 millimeter are actually able to be cleaned out using this gel matrix material. I sort of talked about this, but I think this image here does a good job of reiterating that the materials deposition is all voxel engine driven. And if you're not familiar, think of a voxel like the 3D equivalent of a pixel, which is 2D. So it's essentially, breaking the model down into various finite but tiny regions and then applying materials in different ratios to each adjacent voxel to give a certain property or a certain feel or a certain flexibility, etc. So here you see an example of the voxel information driving a bone component. And we see that this bone is broken up into 4 distinct regions. And then we see the close-up here of each of those regions, kind of showing the different patterning between the different base resins that are used to produce that. Again, these patterns will have a combination of bone matrix, a combination of traditional Vero rigid materials, some tissue matrix, and some gel matrix, all sort of mixing to simulate the exact structure of a typical bone. The software is a very, very key component of this. And we can kind of split the software into 2 distinct areas here. Step 1 is that we need to get the files before we can actually build them in the GrabCAD print software. The part of this solution is not have anything to do with what's commonly called segmentation, or the process for converting MRI, CT data, commonly known as DICOM data, into printable files. That all needs to be done in a third-party software generally. So I think the industry kind of gold standard for this process is Mimics by Materialize. What that does is bring in the point cloud information from a scan. It allows an operator to then partition that out, focus on certain anatomical areas, remove extraneous data, and then separate things based on density, etc. So we have the vascular structures we're looking for, the bone structures we're looking for, the blood pools within those vascular structures, and separate all of those out into separate STLs. Once we get the separate STLs, it's basically printing just like any other multi-body assembly that we would typically see on a J750 printer. Another thing to mention about the segmentation side of things is this can also be acquired as a service. There are many organizations that have engineers dedicated to bringing in data, segmenting out the relevant part, and then giving that back to a customer as usable printable meshes. Again, once we get those usable printable meshes, those are the ones that we bring into GrabCAD Print. We assign their various anatomical, descriptions, and then the software takes in and figures out the fill patterns for those different structures as needed. Here we see the blood vessel cleaning apparatus. What this is the standard CS2P tank that's offered for cleaning Stratasys parts built with soluble supports, but has an add-on with the manifold and these valves that you see there that allow you to direct flow through vascular channels and get those cleaned out. We can clean multiple models at one time. It can handle something from the entire build envelope, and it's really hands-free, labor-free, and it does this without damaging the specimens like we probably would have done a year ago if we were cleaning out really, really tiny vascular structures with a water jet. Here we're going to look at the primary use cases for this system. Number 1 is training of health professionals, helping, there's courses to help, surgeon trainees develop their skills, different ways for, companies to show how their new devices are used to surgical professionals and as part of surgical fellowship programs. The next primary use case is really testing and validating new products. So, if we're working on a new design for a stent placement tool, to be able to test that on something quickly without the expense of obtaining cadavers, doing it in a lab, using animals and doing testing on live animals is very expensive, requires all of the surgical sort of environment between respirators and sensing equipment and monitoring equipment and all of that. Just to really test a new device is very expensive, at a minimum, and wasteful comparatively to printed models. And the last one is marketing and sales enablement, and a lot, giving a way for field sales persons to go to customers or maybe go to trade shows where customers are at and sort of in a hands-on way demonstrate how their new device performs in order to generate that demand and that awareness of their new product and help highlight the improvements over what that potential customer might be doing today. There's a lot of new collateral associated with this new machine, and it's actually, or this new solution, and it's actually rolling out, almost daily here, but there's a couple new case studies for each application that are getting released, some technical application guides showing the best practices for printing models for these specific applications. And Stratasys is working heavily right now on some independent third-party validation with a couple OEM medical device manufacturers, and then also doing it at the same time with research institutions, people that are involved in dealing with children with congenital defects and things like that. We're going to see those coming in the certainly near future, but out right now is this Printing with Advanced Medical Models supplementary user guide. If you can reach out to me, you can actually find it right on Stratasys' website, etc. That is the J750 DAP, Digital Anatomy Printing Solution. This is really, guys, just a start of something that's greater and coming and going to be growing a lot in the coming years. So it's really exciting. If you have follow-up questions, potential applications, you want to see some sample parts, definitely reach out. We can put you in touch with those things. Okay, the next new product that's been launched is now the Stratasys J850 and J835 systems. Looking at the system, you'll notice that it's very similar to the J750, and there's numerous different improvements, but the single biggest thing to point out is the fact that now we're adding an additional model material. Although that seems like a very incremental improvement, the J750 with 6 materials, we can do cyan, magenta, yellow, black, white, clear, for example. What if we want to have a flexible component to that model? We then have to trade out our clear for the flexible, or trade out some color within there for the flexible. And then if the next job wants clear, now we need to do a material flush, a change again. So even though it supported 6, it was really just 1 less than would be ideal for never having to change out, never having to come up with a new configuration, and being able to service virtually all needs with a standard printing configuration. In addition to that existing material channel, they've come up with a whole new cabinet you can kind of see there. I'll talk a little bit more about that in a second. And now there's also a touch screen that's attached to and part of that cabinet. So there's no longer having to push in an additional little desk or some sort of a cart with a monitor and a computer and a mouse and a keyboard on it. We could really drive this printer all from that one space that we see there. So definitely an improvement there. Just looking at some of the stats here, the materials it's going to do is the entire Vero family, and that's all carried over from the J750, J735. It does the flexibles as well and the transparent, although we're going to add the VeroUltraClear, which I'm going to talk about a little bit more in the upcoming slides. For the digital materials, which again, if you're not familiar, what we call a digital material is a material that's comprised of more than one base resin. So it could have anywhere from 2, 3, 4, 5 different base resins that are combining to produce, whether that's a unique color, a unique property, some mix between rigid and a flexible to get a custom shore value. This machine supports 2 of the main support types, SUP 705, which is removed with water jets, and SUP 706, which is soluble. It can be dissolved away or moved with a water jet if you're trying to get a part in hand quickly. The build sizes are direct carryovers from the J750 and the J735. And one thing is it supports a super high speed mode, which is approximately 2 times faster than what the fastest the J750 would have done. So taking a look at the materials, the first major thing is a new 4-kilogram cartridge. In addition to being larger and having a longer unattended runtime than the old cartridges, they're packed more effectively within the machine, less empty space. So, again, we can get more out of that same size cabinet. The sealing on these is much better. So they actually don't even have caps anymore. Unlike the old 3.6s where they had a little cap you're supposed to keep with it, but you always lost. And then when you had them on the shelf in your storage cabinet, inevitably they would drip down and kind of create little dots of resin that you had to watch out for and try to keep wiped up if you wanted your cabinet to stay nice and clean. The new one has a new rubber orifice in there that's really, really sealed. They don't even have a cap offering for those anymore because they're so confident in them. With the new material cartridge shape comes the new cabinet that they fit into. There you see a picture on the screen. And these cartridges are offered in the full line of materials, from the standard Vero Opaque, the Vero Vivid materials, which are semi-translucent, the VeroUltraClear, the flexible Agilis, and the new material Draft Gray, which is what supports the super high-speed mode 3D printing. Here we just see some examples of the realism on this new platform. Now that the Vivid materials are getting really dialed in terms of their digital material arrangements for really good clarities and vibrant colors. The Ultra Clear is allowing things to be really opaque, and we're getting really fine feature detail, things with hyper realism built in. This kind of shows the evolution of design activities that could really be supported with a system like this, where sort of to the top left in the all gray model or the white and gray models, this is where we're just kind of validating a specific shape, a specific feel. Does it look right? Does it feel right in terms of its envelope? Next, as you get through the various designs, we can start identifying different design elements with different colors. We have ways to prototype the layout of things like circuit boards and auxiliary components that might be within a specific device. And of course, the important way to communicate that, right, as we're looking at the layout, where is the board, where is the chip, how do the wires flow through the device, is it efficient, is it easy to assemble? So being able to capture that really allows designers to review and think about those things before committing or getting too far down the design road to where those things can't be changed. As we get to the very bottom right corner of this picture here, we see the final version of that product with the packaging, the product itself inside. We can check the fit and the slide of the lid and sort of produce a very near to the final end use part as we can. And we can do that all in one machine, all with one configuration. So here we see just a comparison comparing the super high speed mode and the draft gray material to the existing high speed modes that we might expect to see on a J750. With this model here, we see that it was roughly 2x in the throughput, and that model that was historically 1 day, 12 hours in high quality or 21 hours in the high mix. The super high speed print time is 11 hours and 14 minutes. So down significantly over anything that would have been done in the past. Again, so just to kind of summarize on the advantages of the J850, is that 7th material bay, no longer having to trade clear for flexible on a regular basis. And the larger 4 kilogram cartridge mean longer unattended run times. The super high speed mode to knock out big, bulky projects just really quickly when all the detail and colors and all that might not be important. And we can do more digital materials in a single build because we have that additional material channel to support that. So there's a lot of really good collateral associated with this product. Here we see the reasons to upgrade documentation, the new user guide, and a design guide for J850. The last product we're going to talk about today is the VeroUltraClear material. We see a little picture of it there on the left-hand side over a brochure, and as you notice, that printed imagery shines right through that block, which is approximately 1 inch thick there. Here we see a comparison of the VeroClear material, the traditional VeroClear that we would have had on a J750, and the VeroUltraClear that's available on the J850. Again, to be very clear about this, no pun intended, the UltraClear is not going to be available on the 750 platform. It's really limited to the 850. So looking at by the numbers, the transmission index, we see that the old transmission percentage of VeroClear would have been at about 75%. And with the new UltraClear, we're at 86%, a lot closer, about 2/3 of the way closer to a PMMA reference sample of the same one. So significant improvement over the old VeroClear. And if you look, the yellow index drops from a 6 to a 1.2, whereas the PMMA reference sample is at a 0.6. So we are 80% of the way there over the old VeroClear. So really the big picture is its outstanding transparency, and especially after we post-process or photo bleach that, 2 of the same processes that we would have done with VeroClear, and those processes are direct carryovers. Some notes for the VeroUltraClear is that it does require the traditional VeroClear to be loaded in order to print the VeroUltraClear. And the reason for that is if we printed just the VeroUltraClear, it would tend to have a tacky or a sticky or a, we'll say, undesirable sort of surface texture and finish to it. So the way they've overcame that is by applying the traditional VeroClear as sort of a shell, and then the VeroUltraClear occupies that center section beyond a 0.5 millimeter or 1 millimeter to the interior of the part. So if we're printing off of STLs, it's going to have that shell be a 0.5 millimeter or roughly 20 thousandths of an inch. And if we're printing off VRML, OBJ, or texture files, that thickness is bumped to 1 millimeter to support some additional sanding and post-processing that we might want to do to it. The new spec sheet on this is out, all the new properties, etc. You can find that right on the Stratasys website. Reach out if you'd want us to provide that directly to you. So with that, that's all I have. Please reach out if you have any questions. Thank you all for participating today. We really appreciate your time and hope you got something value from it.